Hi everyone, it is my great pleasure to welcome Professor Carlos Morales-Guio for today's CIC webinar. So let me give you guys a quick introduction about Professor Carlos Morales-Guio. He received his bachelor degree in engineering in 2011 at Osaka University, and then obtained his master in chemical and biochemical engineering in 2013. And he received his PhD in chemistry and chemical engineering in 2016. After that, he started his postdoc research under guidance of Professor Le Wu, which is focused on the coupling of electrocatalysis to photoabsorbers for solar fuels production. After the PhD, he joined the group of Professor Thomas Stramilo at Stanford University, where he was a postdoc fellow working on the engineering of catalysts for the electrochemical conversion of carbon dioxide into fuels and chemicals. And in 2018, Professor Morales-Guio joins UCLA School of Engineering and as a tenure-track assistant professor in chemical and biomolecular engineering. And his research interests are on the electrochemical catalysis, particularly with respect to energy and chemical transformation for sustainable energy applications. So today he will give us a talk towards understanding the roles of mass transport in electrocatalysis, the role of dimensionless analysis and multi-scale modeling. So let's welcome him again and enjoy his talk.
Okay, Shiyun, thank you very much for the introduction, and Paula, Chong, and everybody, thank you very much for the invitation to present in this webinar. So I will go directly into the meat of the talk. So in our group, we're looking at different processes that are in this envelope of a vision of a sustainable energy infrastructure. So we're working a lot on taking electricity and carbon dioxide and making fuels and chemicals. We're also interested on the reverse process of taking those fuels and generating electricity. We're also looking at using electricity to generate heat, to drive entropic changes and to drive energetically uphill processes as well. And most recently, we're also starting to work on the use of electricity for carbon capture and utilization. So although it might look like as something that is very broad, in reality is that all these different reactions, all these different transformations are underlined by the same physics. The same principles that you can apply for one of these processes actually translate very easily to the other ones. So we look at the phenomena of transport, so mass, charge, and heat transport that are convoluted with reaction in these different transformations. So what we have identified is that the key to a sustainable energy infrastructure is actually the accelerated scale up of electrified fuels and chemicals production systems. So we are focused on scale up and answering questions of what do you need so that you can actually scale up some of these processes. Today, I will speak more specifically to the transformation of electricity and carbon dioxide to make fuels and chemicals. I would like to motivate this talk by pointing out that the challenge that we have is a challenge of scale. The CO2 emissions of one person in LA per year is around 10 tons of CO2 equivalent per year. And one person consumes energy at an average rate of 2 kilowatts, okay? So if you scale up all the way to the US, we have 328 million people. The energy consumption is proportional to that population, and the emissions are also sort of fall on that line. So you have here the LA County, UCLA power plant. So what I want to emphasize is simply that because our energy consumption and energy generation is linked to fossil fuels, we have proportional amounts of CO2 emission. If I put the work that I will present today in this type of reactors, and if I wanted to put them in this scale, they actually are somewhere outside. So the amount of electricity or the power that these systems consumes are very, very small. And the amount of CO2 that they transform is also very, very small. So the question that we ask ourselves as a group is, what will it take to get in the next 5 years to a prototype that is not a few square centimeters in area, but maybe 10 meters? And we believe that if we are able to solve these questions, right, or if we are able to scale up from a few centimeters to 10 square meters, then most likely we will be in a better position to maybe really have an impact by 2040 or so, right? So many of these technologies are projected to, by the middle of this century, but the reality is that in the last 20, 30 years, there has been very little work and very little success in the scale up of electrocatalytic technologies like carbon dioxide reduction using electricity. So what we have identified as the challenge is that there are no fundamentals of how to scale up these systems. Simply, we don't know how to rationally design and rationally increase the size of these systems. In our group, we work on different aspects. So we work on material synthesis and characterization, in cell design and testing. And we also do a lot of multi-scale modeling so that we can actually understand what is happening in our cells. We can parameterize multi-scale models, and then we can use that parameterized model so that we can rationally design systems at a larger scale. What we understand also now is that even though it appears to be a fundamental research, even when we do fundamental research, the complexity of the systems are so high that they are just simply too difficult to understand. And what we have, in a way, is just given up. And we're trying now to accelerate that process of understanding fundamentals and also translating fundamentals into applied research through the use of computers. So towards the end of my talk, I will talk a lot about how is it that we're using machine learning and to sort of scale up these processes. So I would like to point out that as chemical engineers, we look at scale-up processes. And in theory, if you're able to scale up a process, you're also able to scale it down. And in that process of scaling up something, you need to, for example, understand control, have some idea of what is a rational design of a system, and integrate these units into a complete process, right, for product separation from feedstock treatment. And so in that process of scale up, I think there is a relation to the center, the CIC center, right? So if you want to scale up this integrated catalyst that you're developing, obviously if I understand correctly, your center is focused on understanding, right, that spatial and temporal control, how to control reactions at the on time and on space, right, at multiple scales. And then so even if you are very successful in a small scale in your lab, right, I will challenge the students to always think, how do I translate this beyond the lab scale? So this is not scale up, definitely. So scale up doesn't mean just to build reactors larger, right? So we do often see sort of a naive approach to scale up, and the same translate at the way that we do research. So we think that ambient temperature, ambient pressures are necessarily good, but in reality, they are not. I mean, once you move or try to increase the size of your systems, right, the ambient pressure does not make sense. There is a physical constraint, right, of how fast you can move gases through a pipe, right, and you cannot just make pipes infinitely large. So you actually need to compress those gases so you can move mass into with rational speeds, right? If you have, so they can match sort of the catalysis of the reactions that you have. So this is sort of our approach. So we know that scaling up doesn't mean you simply make things larger, right? It actually requires a lot of understanding of the process. So what we use as a tool is dimensionless analysis, okay? And the idea is that in dimensionless analysis, obviously, there is no length, no mass, and no time. So there is no scale, all right? So there are no scale up problems simply because there is no scale, right? So the scale up then is simple. You just simply find your catalyst and you say, my catalyst is perfect when this dimensionless term of Sherwood is 100. And I don't care what is that means in terms of temperature or whatever, right? You simply try to build a larger reactor and make sure that that same dimensionless number is 100. So that's an approach that is typically taken in chemical engineering as an approach to scale up, right? So we just bring all the complexity of the system into one number, and we say, okay, this same number is the one that we will change different parameters, geometries, different things, right? But we will make sure that at a larger scale, that same number is the same, so that we can have certainty that our system or our catalyst behaves identically, all right? So these are some examples of dimensionless numbers that are well-known: Reynolds number, Peclet number, damp color number. So these are things that we use to create correlations and sort of combine different properties of a system into one number, right? So that you reduce the complexity of the system, because many times it so happens that these properties are interrelated, right? So if you change the temperature, you change the density, but that also changes the viscosity, some different properties. And so the use of dimensionless numbers actually helps you to account for all those things that change with temperature, pressure, etc. Okay. So as an example, I will show you how is it that we use this dimensionless analysis to study continuous stir tank reactor. And you can imagine here that we have a reaction. We transform A into B. It's just a first order simple reaction. You have a flow of a reactant, right? And so you have a constant flow rate, and the concentration of your molecules in that flow rate is given by Ca0. So you know how many moles per second are actually going in. And so you have a reactor that is perfectly stirred. And so it's a perfectly mixed reactor. You know the volume, that is V. And at steady state, you can be sure that the concentration of your reactant is A, and the concentration of your product is B. What is very important here is that when we look at in order to keep the volume constant, all the liquid that comes in, let's say, needs to go out. So that means that you will also have the same flow rate at the outlet, so that you can keep a constant volume. And then you will have the same concentration. So what you take at the outlet is representative of the concentration in the species in the reactor, okay? So many times we talk about first order dependence, right? Or a first order process. But if you have a first order process and you use different reactors, so not a reactor like this one, but maybe more like a batch, like the typical reaction cells that maybe you use in some of organic chemistry, right? Where you just have a vessel, there is no mass going in and out over time. So that's what we call a batch process. So even though there you can have the same first order reaction, what you will see is that the rates that you measure are actually different. Okay, so the rates typically of production of products that we measure are a combination of kinetics and also a combination of the reactor. And that is something that is very, very important to keep in mind. So we have to look a little bit at the math of this. So we typically draw a mass balance, right? And we say the amount of molecules of A, that reactor, should be equal to the difference between the concentration of A in the inlet and the outlet, all right? So you can write this mathematically, where V, again, is the flow rate here, and you have the volume. And if you do assume that this is a first order reaction, all right, the first order, the total rate of moles reacted of A will obviously be also a function of the total volume of the reactor. And you can write this equation as Kc for a first order reaction. You do some manipulations, and then you find that there is something that is very important that is called the residence time. Okay, essentially the residence time tells you every how many seconds, right, you will essentially replace the total volume of your reactor. Okay, so because you divide the volume of your reactor by the volumetric flow rate. So this is in liters, for example. The volumetric flow rate is in liters per second. So when you divide them, you have a term that is in terms of units of second. And so here the emphasis of my talk will be that this residence time for reaction intermediates, right, on electrocatalysis is simply not well understood. Okay, and once you actually understand that and take that into account, you will see that that actually determines the selectivity, or yeah, it really explains a lot of phenomena that we were not able to capture in electrocatalysis before. So this is just a little bit more of equations, right? So you can do the manipulation of these equations and you can extract the conversion. Okay, the conversion will be the difference between the concentration of the species at the inlet minus that at the outlet over the initial concentration. And this can be written, if you do the mathematical manipulation, as K tau, where is the residence time, K is the reaction constant here, divided by 1 plus k tau. So here I will introduce then a dimensionless number. So there is a dimensionless number that is called the Dam-Collar number. And for a first order reaction in a CSTR reactor, what that tells us is what is the relative time scale, let's say, for the reaction compared to the mass transport rate. And this is key, again, because in electrocatalysis as well, right? We would like to have an idea what is the relative rates of a molecule coming into your reaction space, right? As well as what is the reaction rate of that molecule, the transformation rate of that molecule. And for a first order reaction in a CSTR, this is k tau. K is the intrinsic kinetics. Tau is just a function of the residence time, the relation between your flow rate and your reactor volume. So you can imagine that you can have the same tau if you double the flow rate, but you double at the same time the volume of your reactor. Okay. All right. And so you can again talk about the conversion in dimensionless terms for a first order reaction. And that tells you that the conversion is just a function of the Dam-Collar number. So this is how we use, if you look at the left and the right of this equation, there are no units. Okay. So the conversion is just a fraction between 0 and 1, right? And the Dam-Collar number has no units because well, if you look at this, they have no units, right? And so here we're describing the process simply in a dimensionless way. For first order reaction process in a continuous stir tank reactor, we can actually determine these dimensionless numbers. And in that way, we can also extract or relate that dimensionless unit that will be the Dam-Collar number, that is that ratio between reaction rate and mass transport, to a conversion. Okay, so if the Dam-Collar number is 1, that means that the time scale for the reaction and the time scale for mass transport are the same. And so you have sort of a 50% conversion. And if it so happens that the Dam-Collar number is larger than 1, which means that the reaction rate is much faster than the mass transport, or the reaction rate outpaces the mass transport, you will have higher conversion of that reactant in this case. Or if the Dam-Collar number is lower than 1, that means that the reaction is actually slower than the transport. Okay. So you can correlate that dimensionless unit to a dimensionless unit that will be the conversion. So why is this important? So in a CSTR, for example, in a continuous stir tank reactor, what you can do, you can imagine, is that if you increase the temperature, you modify K without changing the residence time. So by increasing the temperature, what you do is you increase the reaction kinetics. And for the same process, the same reactants coming in, going out, the volume and the flow rates, you will have a higher conversion just by increasing the driving force. So it so happens that in CO2 electrocatalysis, we start from carbon dioxide that comes from the bulk of the electrolyte. It diffuses, it travels all the way through different layers of the electrolyte. And once you get to the carbon dioxide, you get it to the surface, you make carbon monoxide. And then that carbon monoxide actually is limited by the solubility of carbon monoxide in the liquid, which is quite low. And so typically when you look at reaction intermediates, if you do use electrochemistry, if the molecule has no solubility problems, right, you will expect that this molecule will dissolve and travel away. But in this case, for CO2 reduction on copper, what happens is that carbon monoxide actually binds quite strongly to the surface. So you keep a high surface coverage of CO, and some of that CO still dissolves, but it comes back and reabsorbs because it cannot be transported away at a rate that is fast enough. So the key message here is that the electrode-electrolyte interface is better described as a continuous stir tank reactor where you have perfect mixing. And in the remaining of my talk, what I will try provide is evidence, experimental evidence of why we think that that is actually the case. So we have done different experiments, and what you will see is that this takes the same shape, right? So for the conversion of that reaction intermediate, that is the carbon monoxide, as you increase the driving force, you sort of follow these different lines, right? But as you change the mass transport properties of the cell, you can actually tune the volume of that perfect mixing that you have near the surface of the electrode, and then they will fall into different lines. But once again, you correct for that tau. So in electrocatalysis, in CO2 electrocatalysis, as you go towards the left, you increase the reaction kinetics. So we have done different experiments with different coppers, different copper morphologies. And once actually you account for that description of the residence time of the reaction intermediate, all these experiments actually collapse into one line that tells you that relation between the damp Euler number and the conversion of that CO. And I will tell you how that relates to selectivity. Okay. So these are results, experimental results for CO2 reduction in different electrolytes, so different bulk pH, different conditions. And again, everything just collapsed on the same line for copper, indicating that the intrinsic kinetics, the K is the same. It's just that by changing hydrodynamics in the cell, you see different conversions and different product distributions. So how do we get there? So we develop a gas-tight rotating cylinder electrode cell. So this is the schematics of the cell. Here we have a magnet outside of the cell and a magnet inside of the cell. By rotating the magnet outside, we rotate the magnet inside, and that drives the shaft that contains the active catalyst, that in this case is the metropolic copper. So this is a cell that was developed by Jumbach, and as we increase the rotating speed, right, we actually decrease the boundary layer thickness. So we can control very nicely the hydrodynamics in the cell and the mass transport properties of the cell. If we compare that to typical state-of-the-art electrochemical cells, for these things. So Richard, so I think you're muted, yeah. So if we compare that to sort of state-of-the-art electrochemical cells that we use in our lab as well. So those cells that are static, where the electrode is not moving, they are sort of equivalent to doing experiments at 100 RPM in our cell. So what this means is that if we rotate at 100 RPM, we use this catalyst, we see exactly the same that we see on this cell. But if we change the rotation speed, then you start to see a lot of different trends that are different in selectivity, and it just means that mass transport actually controls selectivity in CO2 reduction. So the way that we do these experiments is we fix the potential, we measure the current over time, and this cell is connected to a gas chromatogram, so we can measure gas products as they are being generated. And we also have a port where we can take electrolyte, so we can do sampling of the liquid phase and through NMR. So this is a video of the cell. So you can see here at the bottom, we have a compartment as well where we can introduce heating or cooling. So we can do electrochemistry at different temperatures. We have, let me see if I can just play this video. So here what you can see is that we're changing the rotation. As we change the rotation of the magnet, the electrode also changes in rotation. And we can slow it down or increase it. So we can also look at the system under dynamic conditions of changes in mass transport. So in this cell, we have bubbling of the gas in the electrolyte. We also have the gas that is coming in and the gas that is going out towards the GC. So what this means is, again, we can simply measure the same catalyst under different conditions of hydrodynamics, different pH if we want. We can change the electrolyte, we can change the temperature, and we can also change the pressure within a small range that can be tolerated by these cells. We're building a cell for high temperature and high pressures in the order of 100 bars to do the same type of electrochemistry. So the hydrodynamics of a system, right, or this type of systems are well described in the 60s and 70s. The rotating cylinders have been fully described. And what is important to note is that we can use the Reynolds number to describe sort of the turbulent regimes that we have in these systems. And what is key to notice here is that in any system, even if it's not a cylinder, if it's not rotating, what you will have at the surface of the electrode is a non-slip condition. So what that means is that the water that is in contact with the surface, right, is viscous and it does not move. it stays static to the surface of the electrode, sort of creating a pocket that maybe help us explain why is it that we see this sort of CSTR type of behavior. Because near the surface of the electrode, really the liquid is very, very static. And as you start to go a little bit out of the electrode, you have the convection, the bubbling, all the cells that most electrochemists use, because we bubble some gas or we have some stir or something, we're creating convection at the in the bulk of the electrochemical cell, and that we cannot visually see it, but near the surface of the electrode, this is actually what is happening. We're creating some turbulence, we're creating some mass transport that goes in and out of the surface of the electrode that help us bring reactants to the surface of the electrode, but that also help us remove reaction intermediates. So we characterize the mass transport properties. We don't need to actually model the complex hydrodynamics of the system, right? We can actually just experimentally measure the sort of combined mass transport coefficient. So this will be the Km value. So that tell us if the bulk concentration is a certain concentration, right? What should be the concentration at the surface of the electrode, because I'm limited by my mass can move as fast as given by this Km value that we can change through the rotation. So there is a dimensionless number as well to describe the mass transfer coefficient, and that is the Sherwood number. So the Sherwood number is the ratio between convective mass transfer and diffusion rates. And so this is also a dimensionless unit. And what is important here is that this Km value can actually be measured experimentally. So what we do is simply we apply a potential until we see that we see a plateau in a current, right? And if you know how many electrons you have in that process, then you can actually determine how many moles you're reacting per second per square centimeter. And because you know the concentration of the species in the bulk, then you can extract this Km value, okay? So what is important here is that we did different reactions. So we look at ferrocyanide reduction. Again, we look at this, as we change the rotation, we look at the plateau in the current. We're just limited by mass transport, and we can extract these Km values for different rotations, even though it's the same molecule. We can do hydrogen as well, hydrogen evolution. So we control the pH in the bulk, we change the mass transport, and we look at the limiting current, and that gives us the Km value for protons. So the Km values are not a function of the RPM, so it changes with the RPM, but the Km values will be different for ferrocyanide or protons or nitride, and that is simply because all these different molecules are riding the same waves, the same hydrodynamics, but each molecule has intrinsically a different diffusion coefficient. And so they, even inside of those waves, they will move faster if they have a higher diffusion coefficient. So we can also do this with nitride reduction. We can quantify the total amount of ammonia, so which is important because you might see a flow of electrons, but that doesn't mean that all your electrons are going into exactly the same reaction. So by coupling these analytical tools to the electrochemical cell, we can actually quantify what is the rate limiting step or the rate limiting rate for the reduction of nitrate to ammonia. And as you change the temperature, obviously that Km value also changes, as I mentioned before, because the diffusion coefficient changes as a function of temperature, density changes, viscosity changes for these systems. What is important is that all those changes, again, can be put into one dimensionless number, that is the Schmidt number, that allows you to account for viscous effects and molecular diffusion rates. And what we have determined is this red line that is sort of a universal line for any electrocatalysis that we do in this system, right? What this means is that any electrocatalysis that we do, they are all riding the same hydrodynamics as we change the Reynolds numbers, as we change the rotation, and as we change the temperature of the system. So what this means is that the system is well characterized, and now we can look confidently at different chemistries, but we know that they are all have the same hydrodynamics. Sorry, I don't know how I'm doing on time, so I lost. Until what time should I? Just
keep going, Carlos.
Yeah, go ahead, Carlos.
Just keep going, Carlos. Yeah.
Okay, so I just wanted to point out that the static cell, right? The typical cells that we use are somewhere here. We reduce the rotation of the electrode, it sort of starts to plateau, and this is simply because in the background we have this bubbling of the electrolyte, right? And that creates a sort of background convection. So yeah, the rotating cylinder electrode allow us to study electrocatalysis under well-controlled mass transport conditions for different reactions. Yeah. So how do we use that for CO2 electrocatalysis? So we typically we use this type of cells, right, where you bubble carbon dioxide, you have water, and you apply electricity, and then you can make a fuel or a chemical, and you also generate oxygen. So typically you have two compartments, a cathode where you make the fuel that you want. You have a membrane that prevents that fuel to come to the anode, where you actually oxidize water to make oxygen. And if you do CO2 electrochemistry on copper, you see that as you see all these different products. We can see more than 16 different products from copper at the same potential. So if you choose a potential somewhere here, you can actually see all these different products being generated at different rates, right? Ideally, we would like to have a system that is very selective to ethanol. And then so the question is, how do you design a catalyst so that you can actually get there? Here in these plots, if you go towards the left, you're increasing the electron energy, and if you go upwards, you're increasing the rate of reaction. So the two CO2 reduction complex or the CO2 reduction mechanism is actually a very complex reaction network. You have more than 100 different species, more than 100 different reactions, and more than 1,000 different pathways for different products. The complexity or the issue that we have in electrocatalysis is that we do 5, 6, 10 experiments, right? We change a little bit of some properties, and then suddenly we will expect to understand the complexity of this network, and that is not the case. To solve or to answer complex questions, you actually need a large amount of data, right? So whenever you're going to make a difficult decision, right, you will try to gather as much data as you can, and the same approach is also true for electrocatalysis. So when you're trying to understand complex reaction networks, you actually need to collect a lot of data. So to simplify that, we have just taken the rates of reaction that we can measure experimentally, because we can quantify all these different products. We know how many molecules of CO2 per second per square centimeter are being transformed to either formate or through CO. So what we know in electrocatalysis is that these two pathways to formate and to carbon monoxide are actually different. So you can take carbon dioxide, make carbon monoxide, and carbon monoxide is the main reaction intermediate for the production of methane, ethylene, and different alcohols. And then R4 will be the carbon monoxide that actually escapes that CSTR space or that volume near the surface of the electrode, and we can also measure that experimentally. Okay. So what we have done is different experiments and quantified those different rates and how they depend as a function of potential or as a function of mass transport properties. So here on the left, what I'm showing is just we fix the applied potential. So we do a lot of experiments under the same applied potential, and we just simply change that Sherwood number. We change the rotation of the electrode, and we have a look at what happens. As we increase the Sherwood number, as we improve mass transport, what we see is that the hydrogen evolution increases. The formate production rate also sort of increases, hits a plateau and starts to decrease. And if you look at that step here, R2, that is this transformation of CO2 to CO, and then CO to further reduced products. But R2 is just this first step. We actually see that that's actually constant as we change the mass transport. So as we change the mass transport, the transformation of CO2 to CO is actually not affected, even though we're bringing more CO2 to the surface of the electrode. So this plot here, what it does is just simply takes that CO rate, the R2, CO and further reduced products, and we will break it down now into the different pathways that you have once you make CO. So R4, R7, R6, R5. As you increase the Sherwood number, you increase R4, that is the transport of CO away from the surface of the electrode. Okay, so CO is the main reaction intermediate. And as you improve the mass transport, right, you actually reduce the volume of that CSTR near the surface of the electrode, and you also sort of increase the flow rate of that CO out. Okay, so you simply improve the mass transport of CO out. And from here, you can also obviously calculate what is the conversion. So at low Sherwood numbers, right, the conversion of CO is quite high because not a lot of CO escapes, but we see a lot of different products that are made from CO. And as you go to high Sherwood numbers, right, you see more carbon monoxide and then less of the further reduced product. So these rates that I'm showing here is number of CO2 molecules being or going through that step. So I'm not looking at moles of ethylene or moles of methane, right? So I'm just looking at the moles of carbon dioxide that were transforming to carbon monoxide and that then went to make ethylene or methane. Obviously, for ethylene, you need 2 CO molecules, right? Yeah, that's what this is showing here. And what we find is that the flux of R4 is actually proportional to the Sherwood number, which should not be surprising. So the transport of these molecules is a first order process. And as we change systematically the mass transfer properties, as we change the Sherwood number, we will expect as well that this is sort of a linear correlation with that CO local concentration. And if you look at the different products, methane, hydrocarbon, oxygenates, right? So these actually decrease. In the current knowledge in the literature, what the assumption is that if you increase the mass transport, you lower the local pH, and then so you should increase the production of methane. But what we see is that actually that's not the case. So even though the pH is lower, as we improve the mass transport, ethylene and methane, both of them actually decrease in the production rate. And we have enough evidence to actually suggest that the pathway for the production of ethylene and methane actually is the same. They do share a common reaction intermediate, and then they use a spread relating, depending on the kinetics, on the relative reactions for a thermal step that will be the CC coupling versus a electrochemical step that will be the addition of protons and electrons to a carbon atom on the surface of the electrode. So with this, we just want to emphasize this is the same driving force, the same applied potential. So when we change the mass transport, we change sort of the mass transport properties sort of far away from the double layer. We're not affecting the double layer in any way when we increase the rotation, right? Because we're just not applying, we're not modifying in any way the potential drop at the interface, but we're sort of affecting mass transport properties maybe 10, 100 nanometers away from the surface of the electrode. And that is actually enough to explain these changes in CO2 selectivity. So again, I will go back to the Dam color number. So we can look at the Dam color number for CO2 reduction to understand whether we're limited by transport of CO2 to the surface of the electrode. And this is possible simply because all these Km CO2 values that we put in these equations are actually extracted from the hydrodynamics of the cell. Because we know very well what are the mass transport properties of the cell, we can account for these values numerically. And what we see is that the Dam color number is actually lower than 1. So that means that we're not really limited by CO2 transport to the surface of the electrode. Yeah, so CO2 reduction is not limited by mass transport. And if we look at the further steps, right? What is key here is that this R4 process is a first order process. So if you change the concentration on the near the surface of the electrode for this carbon monoxide reaction, you should increase the flux. And so what we do now is that we use this R4, this flux of CO that we know that is a first order process, as an internal clock to actually estimate the reaction orders for the other processes. So if this flux that is a first order process is affected in the same way, right, that R7 or R6, then we can create those correlations and understand whether a process is really first order or second order with local concentration of species at the surface of the electrode. When we measured the CO surface production rate, so this is step R2 relative to the transport of CO away from the surface of the electrode, that would be this stamp color number 1 CO. This is shown here as green. What you see is that these values are all larger than 1. And so what it means simply is that we make CO at a rate that is much faster than what we can transport away. And so what that means is that that CO accumulates near the surface of the electrode, and then you have a lot of back mixing, all right? And that is what gives us exactly that sort of CSTR well-mixed volume near the surface of the electrode, right? And if you look at the further reduction rate, okay, so that will be this red line. So what we say is that this is actually 1 over Sherwood square. So yeah, so CO further reduction is limited by mass transfer of CO. And if we look at the further reduction, what we say is that this is actually 1 over Sherwood square. So what we say is that essentially what we say is that the reduction of CO to further reduced products is a function, it's a first order process, and it's also a function of the residence time of that CO near the surface of the electrode. So that sort of matches the kinetics that you will expect for a CSTR volume. Let me just jump to the results. So what we say is simply that, yeah, this is really a first order process on the concentration of CO, but the reactions are the products that you see is actually a combination of that reaction rate, that is a first order reaction, multiplied by the tau, by the residence time, as shown here. So we can separate intrinsic kinetics from mass transport properties or things that you can change with the hydrodynamics. So this damn color number, effectively K, again, is intrinsic kinetics, and tau is just a function of mass transport. Yeah. And so now out of that complex network for CO2 reduction, right? So we actually find that there is actually just one mechanism that can explain the different reaction rates that you see when you change the bicarbonate concentration, when you change. So if your mechanism is correct, right, it should actually be able to explain all the different products that you see or the different rates that you see as you change any condition, whether it's temperature or you change rotation rate, right? So essentially what we have done is taken a lot of experimental data and really use it to narrow down what is actually the rate limiting step in these transformations. And what we identified is that it's very likely that you take CO2, you make CO. That CO is reduced to some sort of carbon, perhaps, species at the surface of the electrode. And depending on what is the residence time of that CO and the probability that that CO is just lingering around at the surface of the electrode, you actually increase CC coupling. And if you don't have a lot of CO, then what happens is that carbon will be further reduced to make methane. And then the same carbon reaction intermediate will be an intermediate for acetaldehyde production and ethanol. So far, we believe that the CC coupling is just 2 CO sitting on the surface. But this is just sort of an explanation, but there is no, there is some spectroscopy evidence, right? But most of the DFT tools that we have right now actually cannot account for that sort of dynamics of absorption and reabsorption of reaction intermediates. And so essentially I think we're challenging what is believed on the CO2 reduction mechanism for this process. And I will just finish now with just pointing out that in that goal of going towards a large scale electrochemical manufacturing processes, we actually have to work a lot on just the sensors, all right? So you have a detector, you have a gas chромatogram that is coupled to your system. How reliable is the information that comes out of there? So once you accumulate big data, you also need to contextualize that information, extract analytics, and that is sort of where we're working in our lab right now. So again, these systems are too complex, right? You need a lot of data used on the same system under different conditions. So you can actually test or prove or disprove some of these reaction mechanisms. So that's where artificial intelligence and machine learning come into play, right? In helping us process a lot of data. So this is sort of the setup that we have. We have the reactor and we have automatized the whole collection and analysis of the current. So the integration of the current, the calculation of Faraday efficiencies, the GC measurements, the analysis of the GC. Now everything is really done in real time as we run the experiments. And so we're right now running on control. So we're sort of changing the set point. For example, we fix a set point for the production of ethylene, and we ask the system to drive the system to a new ethylene production rate. And now the system is well described enough that actually we can take the system, or the system take itself to the new set point for the production of ethylene. Yeah, so this is sort of the big board picture of how our system operates. So we have the reactor, we have different calibration files, right? So we do a lot of product quantifications algorithms, right? So that you can quickly in real time just calculate reaction rates or production rates, and then compare that or sort of fill gaps into these maps of reaction rate versus operating conditions, either potential or rotation of the electrode. And from there, we're starting to build these mass multi-scale models for the same system. All center around this rotating cylinder electrode with the hope that if we parameterize this system well enough, we will have a system or a multi-scale model that we can apply then to design the next scale or the next type of reactors for this type of process. And I will just finish by pointing out that so all the points that you see here are experimental data points. It's the average of 3 different experiments, and all the lines actually come from a first principle model. So I show you so far just the results at a fixed potential, different rotation rates, but you can also do different rotations and different potentials. And what you see is that the same first principle model actually can explain all the different reactions that the different production rates that you get. But again, all this is possible simply through the use of dimensionless time color numbers and the relative relations between processes that are happening in this complex network. And with that, I will just finish by pointing out that you can also actually describe what would be selectivity. So now that you have all these different rates, right, and how they are affected by mass transport or by different conditions, you can actually identify also what will be sort of the optimal conditions to, for example, have the higher selectivity for ethylene. This is for a flat copper, right? What we identified is that the longer the residence time, so the smaller the Sherwood number, and the lower the bicarbonate concentration, the higher or the more selective that your system will be for the production of ethylene. But again, this is all the same catalyst. Just by changing the rotation, the mass transport properties, you actually can tune the selectivity for this for polycrystalline copper. Okay. With that, I would like to acknowledge that this is the work of Junbak, who is, I think, is also maybe here as well. So this is the work primarily of Junbak and Martina. And I would also like to acknowledge the Sloan Foundation for the funding, and CESMI, the Center for Smart Manufacturing here at UCLA, who has provided funding for all the automatization of the reactor. And I will take questions.
Thank you so much, Professor. So I guess we will start the questions from the students and postdocs.
Hey, I had a question on, I really like the talk. It's really interesting. I guess I had a question on, it seems like, I think you mentioned like how you're able to like automate the reactor for testing like different reacting conditions.
Yes.
So I was wondering how maybe if you like take into account like maybe like catalyst degradation over time, or just like with the electrode and stuff.
Right. So yes, that's a very important aspect of our research right now. So we train the system, right, with data that is collected over 1 hour, 1 hour, 20 minutes. But this the control experiments that we run for 4 hours or so. And during those 4 hours, you actually have a lot of degradation of the catalyst and changes in the selectivity. So what we're working on right now is in the system, right, that so that it can retrain itself. as the time passes, right? So you can actually account for the degradation of that system, so that effectively when you're trying to drive the system from one set point to the next, it actually accounts for that degradation. Yeah. So that retraining is based on real data that we're collecting over time, right? Yes.
Okay, cool. And then I guess another, maybe a follow-up question for that would be, have you ever thought about using that degradation data to maybe potentially model the overall catalyst degradation, if that's possible? Or
yes, so the degradation, what we identified right now, the model that we have is that degradation is a function of the integral of the current. So what it means is that the higher current that you have, right, the faster that your catalyst will degrade. So if you go to more negative potentials, probably the faster that you make that carbon intermediate at the surface, right? And the more, perhaps, we believe that the activation mechanism is probably through the creation of some graphitic of some sort of carbon species at the surface of the electrode that is accelerated as you run the system longer and as you pass more electrons. Yeah.
cool, thank you.
So any other questions from students? Okay, can I ask a quick question? So would the shape of the rotating electrode make any difference?
So no. So
Okay.
what is unique, and this obviously we did not know it when we started working with the cylinder. What happens is that the cylinder electrode is unique in the sense that the mass transport, right? As you rotate the electrode, the mass transport is actually happening in and out of the surface, in and out of the surface at each point. If you have looked at the description of mass transport in a rotating disk electrode, you have sort of the flux going towards the surface of the disk, and then the molecules move outwards. And so actually that limits, so essentially your concentration of species is changing as you move outside towards the outside of the disk. So that's why commercially you find disks that are simply always very small, 5 millimeters or so. You cannot go larger because then those effects becomes much more significant. The same, the current distribution in a rotating disk, right? It's actually not uniform. You have very high currents at the edge of those disks, while in the cylinder, the current distribution is actually very homogeneous. And this was described by Newman in the 60s and 70s, and then it was a sort of a hot topic of using rotating cylinder electrodes. So I don't know if you have learned electrochemistry with Newman's book, but we were surprised to find out that in one of the chapters, the paragraph what it says is that people should drop the rotating disk and use the cylinder because it's because of all those challenges that you have. So the cylinder is actually quite good. We did not know. It was by chance that we decided to, for different reasons, we decided to use a cylinder. But now we understand that that the cylinder is actually a much better tool to scale up electrocatalytic processes. Yeah.
Yeah, thank you so much. That makes sense. So any other questions from students? Yeah, Brandon.
Yes.
I was just wondering if you can comment a little bit on what is sort of the next step you plan for either further developing this insight into decoupling mass transport and kinetics and electrocatalysis, or what do you plan to do to use that information to scale up these processes towards what they need to be?
Right. So we're just planning now with the rotating cylinder. The geometry is probably is as good as it will ever get. So we're just working on developing a cell so we can do electrochemistry with rotation of a cylinder at high temperatures and high pressures, because we think that those conditions are actually relevant for industrialization of any of these processes. And then what we're also working on is, I showed the data today for flat copper, but we can also put nanostructured copper, so with different porosity. And by controlling the external mass transport, we can actually decouple external mass transport, molecules coming out from the bulk to near the surface of the catalyst, and also mass transport inside of the pores. So you would like to have a high porous catalyst, right? We know that the porosity, as I showed, the mass transport plays a role on selectivity. So once you also have porous systems, and any industrial catalyst probably will have to be porous, right? So we're now working on not only decoupling external mass transport, but understanding also mass transport inside of the pores and how that affects selectivity. And we are also working on this computed fluid in the multi-scale model of this cylinder, of the rotating cylinder electrode cell, so that we can compare what we see in the model, right, with what we see experimentally, and we can parameterize that model. We want to capture the correct physics at the interface when the hydrodynamics of the electrolyte and the solids, right, so that later we can use that those same parameters to design different reactor designs, different morphologies.
I see. Thanks.
Yeah, Hoptron, go ahead.
Hi, this is Hoptron. Very interesting talk. So I have a question about the catalyst. So here you use copper as a catalyst, right? Mm-hmm. So as I understand, copper is good at producing C2 plus product, mm-hmm. But not good at convert CO2 to CO. So I'm wondering if I switch to another catalyst that has different activity, will we observe? So we will expect to observe different phenomenon of that conversion versus DDA value relationship, right?
Right. So the first thing is that we do think that so intrinsically copper is not as active as gold to make carbon monoxide, CO. But what we have said is that you can actually turn copper into silver if you want, because if as I was showing before, right, as you increase the mass transport of CO away from the surface of the electrode, you actually increase the production rate of CO. So you can actually make copper look as silver if you transport the reaction intermediate fast enough. So here what we're saying is the change of selectivity. So here the selectivity is changing towards carbon monoxide. So it's not that copper is not good at making CO, it's just that it makes CO and you cannot remove that CO fast enough, right? Because you're limited by this desorption and the solubility. But then it's plenty of active to make CO. And then your second question was that, sorry.
Oh, I assume if we change the catalyst, this relationship will change.
Yes, so that's the idea, right? So we started from the point that we want to first understand polycrystalline copper, right? So there are many new catalysts that are proposed as more selective or more active than copper. But what we understand now is that it's just a matter of the morphology, right? So the morphology is the same. The morphology is different, and you see different product distributions. And also many times when you add gold or silver, what you're doing is just changing one parameter, right? You're not changing intrinsically the activity of copper, but maybe you increase that CO concentration at lower potentials, right? Because now you have something that is better at making CO. And then that CO concentration at earlier over potentials changes your selectivity. But what we see now is that we can describe that again with the same intrinsic kinetics of copper. Understanding that, you have something that produces more CO perhaps,
Okay. Yeah, thank you.
And is there any other questions from students? If no, I'll open the question to faculty professors. Yeah, go ahead.
Hey, Carlos, wonderful talk. Very solid, and I really love the whole design. So my question is about automated the exploration. When you are you trying to use Bayesian optimization to map the space during the testing? That's my understanding about what you're trying to do. Is that right? Or
yeah, so we have so when you use machine learning, right, you can create different neurons and different layers, right? And so what we're trying to do now is just simply match that sort of new neuron description to a reaction network.
Okay.
because that's something that you can do. So we're trying to combine first principle description of a process with the description of those networks, because we think that the network, right? You can use the same network, yeah, but match it in different morphologies of the catalyst.
So you are thinking about that the foundation of a neural network is still based on first principle calculation, because the first principle is the first principle calculation to give you the starting point or of the neural network about reactivity, or it's not, or everything is empirical.
Right. So we're coming from both sides. So we have a lot of experimental data that we're using to build a first principle model. And we also have just a machine learning system, right, that can describe the relation between inputs and outputs. And what we're trying to do is now bring them together, right? So we're coming to the problem from both sides.
Okay.
But to actually marry that first principle model with the complex neural network, what you require is a lot of data.
Yes.
Data.
I see. And maybe should I just a side question is how translatable, if you, because I know your current focus is CO2 fixation now, how fast, how translatable your setup is to automatically optimize reaction for other catalysis, say nitrogen fixation or methane activation, which my group works on it.
Right. So it's more a matter of so CO2 and methane are very easy to do in the same system, because you have the products are gases and the gas products are the same. CO, CO2, if you make methanol, you can also quantify the liquid. So we have been also using for methane partial oxidation to methanol. Nitrogen reduction, we haven't done yet, because we think that you have a problem with the solubility of nitrogen.
Fair. Okay.
You will want to do it probably high temperatures or high pressures at least, right? And then we do nitrate reduction because it's easy to put nitrate into the solution, and then we make ammonia. So it's more a matter of what analytical tool do you need, additional analytical tool to quantify products. But if it's things that you can quantify with the GC, I mean, we're doing it. Yeah.
My experience is, even for the case of methane activation, you may be able to get ambient reactivity, but high pressures sometimes are also needed. For another reason is solubility, right? I know the rotating rod and rotating cylinder electrode helps to mitigate that, but still, the solubility of methane is different compared to carbon dioxide. So I appreciate. I think the high pressure will help even in that case. Yeah, but really fantastic. Yeah, thank you.
Thank you, John.
Yep.
Hey, Carlos, that was great. I think I'm asking a similar question to what Chong was just talking about, and I'm thinking about the sort of fashionable use of gas diffusion electrodes in electrocatalysis, and whether you've sort of modeled the mass transport from the gas phase reactants into solution, and whether that's limiting in some cases, and how it compares when you're whipping this cylinder around to getting high local CO2 concentrations relative to these other methods that are in use. It'd be great to just hear your sort of thoughts on the differences and similarities. This is me not knowing much about the cylinder electrodes, but it seems like really cool technology.
Yeah, so when something that we use is sort of a boundary layer thickness to describe the mass transport. And what that means is how far is the bulk of your concentration of your electrolyte from the surface of the electrode. And here, when we change the rotation, we can change that boundary layer position. It's just a relative number, but between 100 micrometers maybe to 20 or 30 micrometers. So that sort of tells you, if you rotate very fast, the boundary layer that you get is maybe 20 micrometers. So the bulk of your electrolyte can come as close as 20, 30 micrometers. In a gas diffusion electrode, those distances could be 1 micrometer. Or maybe less, nanometers, really, because you actually really bring that interface between the gas, the liquid, and at the interface. So if we were to rotate the electrode, we rotate it between 100 RPM and 1,000, 2,000 RPM. That will be the equivalent of rotating to 30,000, 40,000 RPM, which it's, so what that tells you is that we cannot match the rates of gas diffusion electrodes on a rotating cylinder, but that's not the purpose, obviously, right? But then what we see is that you can actually, the same first principle model, once you understand what are the Sherwood number for the mass transfer of CO2 from the gas to the liquid to the solid in a gas diffusion electrode, everything that happens inside of those pores, because you have sort of pores when you deposit the copper catalyst on the gas diffusion electrode, are actually in the same time scales as what we see in our porous electrodes. So the residence time of that carbon monoxide intermediate inside of the pore is what actually determines the selectivity for the different products that you see. So we can translate the results on a flat polycrystalline cylinder all the way to the gas diffusion electrode, but that requires, but we cannot reproduce them in the cylinder. Yeah.
Thanks.
Mm-hmm.
Ja-
Hey, Carlos, that was really, really great. Thanks for the lecture. And my question is, I'm wondering about surfaces that may change their identity as the reaction proceeds.
Mm-hmm.
Maybe not, you talked about decomposition, but there are other things I'm thinking about. Can your models incorporate such changes, and can you understand how mass transport evolves as surfaces evolve during catalysis?
Yes, but that will require some microscopy coupled to the changes, right? So if you have sort of destruction of the porosity, I mean, if you have some experimental method, right, double layer or something that you can measure as you run the experiment and as the system degrades, that is something that you could use as a sort of an indicator of how is the morphology changing. Surface rearrangement, atomic surface rearrangement is obviously something that we cannot measure experimentally, right? You can do a spectroscopy. So you can correlate. It will require, to understand and come up with a mechanism, you will require a good amount of data.
You need an independent measure then to kind of provide you with a, I don't know, correlation for inclusion in your models, or?
Yeah, so I mean, if that is, if you really think that the morphology is changing or the roughness is changing, and that is what is driving your process.
What about even like the surface identity in terms of hydrophilicity and hydrophobicity?
Hydrophilicity and hydrophobicity obviously change how is that you dissipate that energy when you rotate the cylinder, and how the hydrodynamics change. Unless if you can measure that somehow with double layer capacitance, that's something that could be possible during the experiment. But then again, you have to go to some different technique outside of the system, to get an idea. Yeah.
Okay, thank you.
Mm-hmm.